Hello and welcome to this series of lecture video. This is the second video on ion exchange chromatography. It is from paper 4 and unit 3. What you will see in this video is principle of ion exchange chromatography, classification of ion exchange chromatography, and the types of exchanger used, their synthesis and their conditions under which you are supposed to use these exchangers. This particular slide explains you the entire principle of ion exchange chromatography in one slide. So what you see in this slide is, you can see over here, this is the exchanger typically shown for better understanding. It may not be actually like this. So what you have is the resin part, and to the resin part you have some functional group attached. Now the functional group may have a negative part and a positive part. Say for example SO3H, which is a strong acidic group. So if you look carefully in all the diagrams where the resin has been represented, you will see the resin part is there and the negative part is there, whereas the counter ion you will see changing. So what is actually happening in any ion exchange chromatography? From the name itself you can understand that exchange of ion takes place. And this exchange of ion is basically responsible for the separation of mixture of ions. So this is a typical situation where you have a sample which is made up of mixture of cations. So I have shown 3 different cations, and these cations have been represented here, and this tells you about the adsorption strength of these cations. So the green one has higher adsorption strength, followed by the red one and then the blue one. And these are the ions that are there on the resin, all having equal charge and all are same ions. Now what is happening in the first step is, when you put your sample, these ions are replaced by the ions from the sample that you're putting. So this is exchange happening. Now while the exchange is happening, it is very important that the electrical neutrality is maintained. We don't have to do anything, the ion itself manages. So what ion does is, the ion exchanger itself manages by exchanging equal number of ions as the number of ions coming from the mobile phase. So what you see over here is that the exchange of ions has taken place. So the earlier ions have been replaced. So H plus ion has been replaced by the cations from the sample, and then they are shown at different level depending upon the adsorption strength. So this is the SO3 minus H plus group, where the H plus ion is the counter ion which can easily get exchanged with the ions from the mobile phase or from the sample. So it's a mobile ion, and since we are talking about cation as a mobile ion, it's a cation exchange resin or cation exchange chromatography. Now after all the ions have gone onto the column, the next step is elution, where you can take out the desired ion rather, as per your choice, by selecting a suitable mobile phase. So in the process of elution that is shown in the third one, you can see that the blue ions are replaced or blue ions are eluted. This process is called as elution, and the separated ion or the fraction that you collect is called as eluate. The mobile phase or the liquid that you're going to use to take out the ions is called as an eluent. So you put a mobile phase, what happens is that ions from the mobile phase will come and take place here, and then the equal number of the plus ions that are there, blue ions are there, they will be eluted out of the column. So this continues. So after blue ions have come out, then the red ions will come out, and then the green ions will come out. So this explains a cation exchange chromatography. If you want to explain the anion exchange chromatography, it will be exactly opposite. The positive charge will be the fixed charge and the negative charge will be the mobile charge. So mobile charge, that is negative charge. So that is called as an anion exchange chromatography. Now we'll see how the anion exchange chromatography is classified. It is classified based on the exchanger that you are going to use. So it is classified as a cation exchange chromatography, which is used to separate cations, and then anion exchange chromatography, which is basically used to separate anions. Now when you want to separate cation exchange cations by using cation exchange chromatography, you have two choices. You can either use a strongly acidic cation exchange resin, or you can use a weakly acidic cation exchange resin. So as you can see over here, the resin part may be same or may not be same, but what is important over here is that the functional groups that are there, in this case it will be sulfonic acid group, and in this case it's a carboxylic acid group. And we all know that organic acids are weaker as compared to the mineral acids. So this is a stronger group and this is a weaker group. What it means is that when you're using this resin in water, this can easily dissociate to give you H plus ions, whereas this cannot easily dissociate to give you H plus ions. So you need to have a pH higher than 7 so that this H plus ion is freely available. Similarly, talking about anion exchange chromatography, and in anion exchange chromatography again you have a choice of selecting a strongly basic anion exchanger resin or a weakly basic anion exchange resin. Now how do they differ? The functional groups are shown over here. Here the functional group will be a quaternary ammonium group, where the counter ion or Cl minus ion is the anion that can get exchanged with the ions from the mobile phase. Here as you can see there are no charges, so in order to introduce charges in the functional group you will have to treat with an acid. So the moment you treat with an acid, it is going to give you something like this. So it also gives you a positive N plus and a Cl minus. So now it can be used for exchange of anions. Cation exchange resins used to separate cations. Now suppose you have a scenario where you want to separate the mixture of ions that are mentioned over here. How do they differ in their with respect to each other? They differ with respect to each other that they have different charges. So this is univalent, this is divalent, this is trivalent, and this is tetravalent. So cation exchange chromatography can be used for separation of ions, so cations, irrespective of their charges. Now the strongly acidic cation exchange resin that we were talking about in the earlier slide is prepared by mixing styrene and divinyl benzene. This is a typical ratio to maintain the cross-linking, are copolymerized in an aqueous emulsion to give styrene divinyl benzene. The resin beads are then sulfonated to give negatively charged sulfonated ions, are firmly attached to the resin and are balanced by hydrogen ions, and these hydrogen ions are active or the mobile cations. So this is typically the way in which we show a strongly cation exchange resin having sulfonic acid as a group. So if you're putting sodium chloride solution into the resin, the sodium chloride solution, when we add, what happens is that you can see H plus ions are replaced by equivalent number of sodium ions. So it is a stoichiometric exchange. That means for one hydrogen ion, only one sodium ion will get replaced. Similarly, when you have calcium ion getting exchanged, so obviously calcium has +2 charge. So for one calcium ion, 2 H plus ions have to get replaced. Now let us see what is the typical structure of this resin that you are using. This is a resin, this is styrene and this is divinyl benzene. So it is copolymerized and then followed by sulfonation reaction. So at the end of it, the resin that you obtain will have sulfonic acid group. So this sulfonic acid group is actually responsible for the nature that is shown by the resin. So it's a strongly acidic cation exchange resin. Moving on to the next one, that is a weakly acidic cation exchange resin. It is prepared by copolymerization of methacrylic acid and a small amount of divinyl benzene to give porous beads. And these beads basically have free COH group and have a weakly acidic property. So one needs to understand that whenever you have a weakly acidic group, it cannot function at pH 7 or at under neutral pH. You need to have a pH that is lower than 7 in order to ionize, higher than 7 in order to ionize the COH group. So that's the reason the ion exchange equilibria that is shown over here. When you add sodium chloride in the earlier one, you had seen that the sodium can get exchanged with H plus ion. But in this case, the sodium chloride ion does not show any exchange. The reason is that sodium chloride is neutral. So the pH is neutral. At neutral pH, it is not going to show any exchange. But if you look at the sodium hydroxide, when you add, you can see that the exchange is happening. The reason is quite clear, that the pH is now in this case above 7. This is a typical polymer that you see, which is used for weakly acidic cation exchange resin, and this polymerization process will give you a resin which will have COH group and can be used as a weakly acidic cation exchange resin. Moving on to the anion exchange resin. So very similar to your cation exchange resins, you also have anion exchange resins, and it is used to separate the anions irrespective of its charges. So you have strongly basic anion exchange resins and you have weakly basic anion exchange resins. And it is prepared by copolymerization of styrene with little amount of divinyl benzene, followed by chloromethylation at the free para position, and the reaction with trimethylamine gives quaternary ammonium salt and equal number of mobile ions. Now this is a quaternary ammonium salt group, and you will have equal number of the mobile ions, that is chloride ions in this case. Now when you put sodium hydroxide in this case, obviously the anion will get exchanged and you will have the chloride ion getting replaced, and in place of chloride ion you will have hydroxide ion. If you have a divalent anion, obviously it needs two groups so that the electrical neutrality is maintained. This is a typical synthesis or the polymer, and you can see the functional group that we require is at para position. So this is a functional group in an anion exchange resin. Moving on to the next one, that is weakly basic anion exchange resin. Now what you see in weakly basic anion exchange resin, the synthesis is almost same, but in order to convert the functional group into tertiary amine group by a reaction with dimethylamine and followed by treatment with HCl is required. The weakly basic anion exchange resin contains very little OH- ions in basic solution as well as in neutral solution. So in order to have more number of OH- ions or Cl- ions, in water it will have OH- ion, but the number of OH- ions will be very less, as we know that dissociation of water is 1 into 10 to minus 14. So the OH- ions are very less. If you want more number of anions to be present, you have to treat it with HCl. So weakly basic anion exchange resins can function well at a pH below 7, whereas weakly acidic anion exchange resin will function at a pH above 7. This is a typical exchange reaction that is shown with nitrate ion. This is the resin, and after treatment, these functional groups are introduced, and after treatment with HCl, it gets converted into a form which can be used for an efficient ion exchange chromatography. In the next video, we will see ion exchange equilibria and factors affecting ion exchange chromatography. Thank you.